In this article, we propose a method to discover prerequisite structure for intelligent tutoring systems. So our motivation actually lies in the CARE project, which proposes a robot coach for physical rehabilitation. The idea is to evaluate from a movie, a picture, human movement, extract from images human poses, and be able to assess quality of the movement. So this led to a clinical study with the hospital of Brest that was carried out for 2 years. In this article, we want to show that the robot coach for physical rehabilitation not only can assess and evaluate human movement, but can also have exercise recommendations, which means that the therapist will propose a set of exercises, like here, 5 exercises, for the patient to train on during the week. And the robot will decide on a day-to-day basis for each time step which exercise to use. So to be able to do that, he will need to use data from example recommendations that proposed exercises in a certain order through time, like here, exercise B, then D, A, C, etc. And what it needs to do is to be able to predict, given the order of exercises it proposed, what is going to be the performance of the learner on a proposed exercise. So given that the learner failed on B, then on D, and succeeded on A, etc., what will be his performance on exercise D? So more formally, an intelligent tutoring system is a system that can provide personalized recommendation of exercises to learners. So an intelligent tutoring system should propose exercises that are not too easy nor too difficult. So this idea resonates with the theories of intrinsic motivation that come from developmental psychology and developed into computational models that try to maximize the learning progress for the learner. It also resonates with the idea of zone of proximal development, ZPD, that is defines a dynamic set of activities that maximize the learning progress. So, for instance, we can look at how we can propose exercises that would be best for learners, that are not too easy, not too difficult. But to do that, we need to understand the knowledge structure. So the idea is that we have exercises, but each exercise actually trains specific skills that are called knowledge components. So for instance, here we have a set of 4 exercises, and they train 3 different knowledge components, and each exercise can train one or several knowledge components, and several exercises can train the same knowledge component. What we are interested in is the prerequisite relations. The idea is that some knowledge components need to be mastered before training on other knowledge components. So for instance, we should learn how to master addition, knowledge component before trying to learn about multiplication. So there's a prerequisite relation between addition and multiplication. And if we know that prerequisite relation, then we can predict the performance of a learner on the proposed exercise based on the relationship between skills. So our question is, how can an ITS learn which exercises to recommend from learner data? To do that, we propose first a PKT algorithm, which is used to uncover unknown prerequisite relations between knowledge components. The second part is the ZPDES-KS algorithm that is used to recommend exercises based on the estimation of the zone of proximal development, ZPD, of a learner according to the uncovered prerequisite relations. So let's dive into the first part, the knowledge component structure discovery with the PKT algorithm. So we suppose that skill level of each knowledge component can be updated after each success or failure on exercises. So from data, experience of students on different exercises, we can estimate the skill level lambda of a student S for knowledge component K at time t as equal to mu, the initial skill level, plus alpha, a constant, times S, the number of times he has succeeded an exercise related to that skill K, plus beta times F, which is the number of times the learner S has failed on exercise related to the knowledge component K before time t. So let's come back to our example where we have 4 exercises related to 3 knowledge components. If we start by saying that we initialize lambda for these 3 knowledge components to these values here, then after failing on exercise D, we can update because exercise D is related to KC3. Then we can update and the lambda for KC3 has increased a bit. After succeeding on exercise A, then we can update and see that because exercise A is training on KC1, then the lambda of KC1 is increased. And after succeeding on exercise A again, then we increase again the lambda of KC1, etc. And this is how we update our estimation of skill level of the student according to his curriculum. We also suppose that the knowledge components can be discovered and can be represented as a graph. So initially, the graph of all these 3 knowledge components is all connected. And through data, we are going to update how important each connection is truly in this prerequisite relationship. So we use a differentiable structure discovery algorithm to learn the structure by gradient descent. So we first suppose that we have relationships that represent the probability that K is a prerequisite to L K and L being each a knowledge component. And by sampling this graph from structured parameters using Gumbel softmax straight-through estimator, we obtain this graph here that is simplified. So we have removed a few connections, and so we can then use success probability on one exercise that we can estimate based on the soft mean of skill levels of corresponding cases and parent cases. So here, for instance, we can estimate the probability of success on exercise D that is training on KC3. We propose a formula where the probability of success is going to be a function, a softmax function that is related to the soft mean of the level that we estimated. So we propose here the algorithm PKT that is using some hyperparameters that can be optimized in order to minimize the binary cross entropy loss between the predicted probability of success and the observed probability and the observed success. The second part of our work is on the exercise recommendation using the ZPD-ES-KS algorithm. So it's an algorithm that we adapted quite straightforwardly from ZPD-ES. The idea behind the ZPD-ES algorithm is that we build a pool of exercises to recommend, which is the zone of proximal development. And we update the pool of exercises based on the knowledge structure. So here, ZPD adds new exercises when a new knowledge component is unlocked, and it removes exercises when the knowledge components become too easy. So let's illustrate it with our example. We have here 5 exercises that are related to 3 knowledge components. So we first will propose to the patient exercises that train knowledge components that don't have any prerequisite. So here KC3 is not yet proposed because KC2 is not mastered yet. So it means that we can propose exercise 1, 2, and 3 to the learner. So this is the initial ZPD that contains only 3 exercises. But little by little, as the learner trains, he will get better at exercise 1. So the exercise 1 is validated, which means that the student has a level above a certain threshold. And this means that we can consider that KC2 is validated. And if KC2 is validated, then we can move to the next level of knowledge components. So we can move to the KC3 and add exercises 4 and 5 to the zone of proximal development. As we here can propose all 5 exercises, we have the student who continues to train and get better. When exercise 1 becomes too easy for the learner, so he's getting much better, then this exercise is deactivated and removed from the zone of proximal development. So our algorithm, ZPD-ES-KS, proposes exercises inside the ZPD that are recommended using a multi-armed bandit algorithm with a reward based on an estimated learning progress. So we suppose that the reward in for the multi-arm bandit is going to be equal to the estimated success rate at time t minus the estimated success rate at time t minus 1. So the progress is the difference between the two success rates, and this constitutes the reward. More specifically, the estimated success is going to be weighted sum between the estimated success at time t minus 1 plus alpha times the observed success at time t. Based on these two algorithms, we show here the results. First result is that our algorithm PKT can uncover the prerequisite graph. So we use for that synthetic data that implements prerequisite structure, varying learner profiles with varying exercise difficulty, and a mechanism to represent learner forgetting. We use 10 random environments with 400 random simulated learners. And from that, we can compare the ground truth graph that is used in our environment and the graph that is uncovered by our PKT algorithm. For instance, here we can see that the graph PKT that is found by our PKT algorithm looks like the ground truth but has a slight difference. For instance, this connection here. And if we compare then our algorithm PKT to other algorithms, so we can compare it to the algorithm kappa index. We compared it to deep knowledge tracing with heuristic, but also structure-based knowledge tracing with heuristic and structure-based knowledge tracing using the adjacency matrix. And from that, we show here the average graph prediction F1 score and final learner level at the end of the tutoring with ZPD-ES-KS. So if the ground truth of the knowledge structure is known, then we have the highest score. But if it's not known, then we can see that our algorithm PKT gives the highest scores in terms of F1 score and of final level for the student. And this is true both when the learner forgets between exercises and without forgetting. The second result is on the algorithm ZPD-ES-KS, and this algorithms outputs a recommendation trajectory, a recommendation curriculum. So here we show the results of ZPD-ES-KS algorithm with one of the data sets with the knowledge structure discovered by our PKT method. So on the left, we have the evolution of learner skill over time. So here we have 10 skills that are estimated. So we have the average level on the y-axis, and the x-axis represents time, the number of exercises trained. And we can see that all KACs increase, so we train and the student learns on all skills. On the right, we have the x-axis, which still represents time, the number of exercises trained, and the y-axis represents each of the knowledge components, and we represent here the evolution of the set of activated knowledge components over time. So we can see that in the beginning, the knowledge components activated are 1, 3, 8, and 9, for instance. And in the end, we see that the most activated knowledge components are going to be knowledge component 10 or knowledge component 4, which is activated much later. And actually these correspond to the knowledge components that increase later on the right hand graph. So this shows that the knowledge components are activated when they increase and are deactivated when they are above a level. We evaluate all the knowledge structure discovery methods according to their corresponding tutoring system by measuring the average proficiency on all of the knowledge components for 300 simulated learners practicing for 300 iterations. Then we compare ZPDES-KS versus a model-based tutoring, so not using the zone of proximal development. And here we show the evaluation of the tutoring models. So with ZPDES-KS and with model-based tutoring. If the ZPDS knows the ground truth of the knowledge structure, then we have the best results. If not, if we have to learn that knowledge structure, then we have the algorithm PKT that gives the highest average level and final level. This shows that ZPDES-KS is better than model-based training. So the zone of proximal development helps exercise recommendations. The knowledge structure uncovered by PKT is the best to infer the ZPD for ZPDES-KS. In conclusion, we can say that we propose a differentiable structure discovery method and it can discover prerequisite relations among knowledge components. And the algorithm ZPDES-KS can exploit this structure to improve exercise recommendations. So in future work, we will work to accelerate structure discovery. Still, there are a few open problems. First, we want to study the data efficiency of the method, how many students need to be sacrificed to get data, exploratory data, from which we can learn the knowledge structure. Second, we need to improve the data efficiency for artificial curiosity methods. And third, we need more recent knowledge tracing methods modeling the prerequisite structure to improve our algorithms. So these are a few references used in this presentation. Thank you for your attention.